Hello learners, in the previous session we discussed about how to determine acceleration using position time and velocity time graph. Also we studied to plot acceleration time graph using the information of position, velocity and time. Now let us continue our discussion. Can we determine the displacement with the help of velocity time graph? Yes, of course, we can determine the displacement using velocity time graph by determining the area under velocity time curve. So, let us see how we can determine by taking a simple example. For this, I consider a simple example wherein I consider that a particle is executing uniform motion, that is, it is moving with a uniform velocity u between the time interval of, let us say, t is equal to 0 to t is equal to t time. This is how we plot the velocity time graph. So, along the x axis we take time, along the y axis we take the velocity, and since the velocity is uniform throughout the motion, we obtain a parallel line for velocity parallel line to time axis. So, between this time duration of 0 to t time, the velocity is u throughout the motion. Now, let us find out the area under this curve. So, for this we need to determine the area of this rectangle. So, let us determine the area of the rectangle. So, what will be the area of this rectangle? You know, rectangle, for the area of rectangle we multiply length with its height or length with its width, whatever the multiplication of the two dimensions. So, here one of the dimension is the length we can take to be t minus 0 multiplied by its height, or the other side is u minus 0. So, finally we obtain u into t. Yes. So, this is the product of velocity with time, and we all know that the product of velocity with time gives us the displacement of the particle in that time duration. So, that is how we can say that this area of the rectangle or this area under the graph, the area under the velocity time graphs represents the displacement between that particular time duration. So, here this is the distance, we can denote it by s, or we can also denote it by x is equal to ut. We can also verify it dimensionally, you know. Here if we multiply the dimension of this time axis, that is t, with the dimension of the y axis, that is u. So, that is LT minus 1. So, what do we get? We get the dimension of length, and that is the distance. So, that is how we say, we can say that the area under the velocity time graph represents the displacement. Now, let us take one more example. A graph of velocity versus time of Ritu going to school by cycle from her home is shown below. So, this is a velocity time graph of Ritu, who is going to school by cycle from her home. So, we need to describe the motion of Ritu based on the graph, and secondly we need to plot the graph for her acceleration. Now, let us study this VT graph. A graph of velocity versus time of Ritu going to school by cycle from her home is shown below. So, here you can see a velocity time graph. So, this is a graph which is plotted for the motion of the Ritu, who is travelling from school, who is travelling to school from her home, and here we need to describe the motion of Ritu based on the graph. Secondly, we need to plot the graph for her acceleration as well. So, first of all let us study this graph. Look at this graph. Along the x axis we have time, along the v axis we have velocity, and if we divide this graph, if we just divide this graph into the 3 time intervals, let us say this is 0 to t1, this is T1 to T2 and this is T2 to T3. So, what I have done here, I am just going to study the entire motion in 3 time durations. Now, let us talk about between the time duration of t is equal to 0 to t is equal to t1. What we may conclude just looking at the velocity time graph. Here we can see that during the entire motion from time 0 to t1, the velocity of Ritu is constant. So, can we say that during this time duration from time 0 to time t1, the velocity was uniform. So, it is a uniform motion. The motion is uniform where the velocity is same. So, this represents uniform motion. Now, let us talk about the another time duration t is equal to t1 to t is equal to t2. Yes. Now, look at this. In this time duration, you can see that the velocity is decreasing. Velocity is decreasing in the time interval of t1 to t2. So, and also since it is a straight line inclined to time axis, we can say that this is the case of deceleration. The velocity is decreasing at the uniform rate. So, it represents constant deceleration. So, it is a constant deceleration. Constant deceleration during the time interval of t1 to t2. Now, let us talk about the third time interval of t2 to t3. T is equal to t2 to t is equal to t3. During this time interval again we can see that initially the velocity was somewhat here, but finally when the time is t3, velocity comes to be 0. Again it represents a uniform deceleration. A uniform deceleration because again we can see that it is a straight line. The velocity time curve represents a straight line which is inclined to time axis. So, it has to be uniform deceleration in this duration also. It is a constant deceleration. Then what is the difference between the deceleration of time interval t1 to t2 and t2 to t3? So, please pay attention over here. Just look at the slope during the time interval of this is t1 and this was t2 and this was t3, right. Now, just compare the slope during the time interval of t1 to t2 and t2 to t3, which has a greater slope. So, we can see that the slope is greater during the time duration of t1 to t2. So, what does it represent? We know greater is the slope, greater is the acceleration or deceleration. So, we may conclude that during the time interval of t1 to t2, the rate of deceleration was greater with compared to the rate of deceleration between the time duration of t2 to t3. So, herein both of these time durations T1 to T2 and T2 to T3 are although representing constant deceleration, but there is a difference in the rate. The rate of deceleration is more in this time duration because of the steeper slope. Now, let us plot the graph for her acceleration. Suppose I consider time along x-axis and acceleration along y-axis, and I also just label the time durations as t1, t2 and t3 starting from 0 time. Now, let us plot the acceleration time graph for the time interval of 0 to t1, wherein the velocity is uniform. So, since the velocity is uniform, we may conclude that acceleration has to be 0. So, in this duration, we get a line, we plot a graph which is overlapping to time axis, since acceleration is 0. So, it is overlapping the time axis in this time duration of 0 to t1. Now, let us talk about between the time duration of t1, t to t1 and to t2. In this duration, acceleration is uniform. So, suppose I consider this to be the acceleration in this time duration T1 to T2, again acceleration is constant, acceleration is uniform. So, it has to be a parallel line to time axis. Now, let us talk about the final time interval from T2 to T3. Again, it is a constant acceleration. So, again the graph need to be parallel to time axis, but what is the difference in this T1 T2 and T2 T3? Now, just comparatively we do not have the exact values. So, we just compare that it has to be lesser. The value of the acceleration has to be lesser. We can just drop the perpendicular over here. So, this is comparatively the lesser value of the acceleration between the time duration of T2 to T3. Again, for our reference only, for a clarity only, I just drop the perpendiculars with the dotted line over here just to study it well in more clear manner, that this is how the acceleration is different at different locations. So, 0 to T1 it is 0 acceleration, T1 to T2 acceleration is comparatively more with respect to the acceleration between the time duration of T2 and T3, but the acceleration in both the durations are uniform. So, what do we study from this simple graph? So much of information we can obtain. It is a simple velocity time graph with the help of which we have compared the acceleration, where the acceleration is more, where the acceleration is less, by comparing the steepness of the curve, and where the velocity was parallel, the velocity graph was parallel to time axis, we can conclude that in that region acceleration has to be 0. Although it is not asked in the question, but we can even determine the total displacement. How can we determine the displacement? Again, if we find out the area under this graph. So, this complete area, determining the area under this curve, we can determine the total displacement of Ritu from her home to her school. Now, let us observe this graph. This is a position time graph wherein we are just going to compare the velocity during the 3 time intervals, that is plotted as 1, 2 and 3 and is indicated by the shaded region in this graph. Now, let us compare this first, second and third time duration. In this, just look at the slope. We know that velocity is determined by the slope of the position time graph. So, just compare the slope in the 3 time intervals 1, 2 and 3. If we look at this, during the third time interval, the slope is steepest. We have the steepest slope and the slope is least during this second time interval, right. So, we can say that the velocity is maximum during this third time interval and it is minimum during the second time interval. Same way, we can also determine the sign of the velocities. So, herein if we look here, just look at this graph again. Here the displacement is negative in this third time interval. So, velocity is negative in this region, whereas in this first and second time interval velocity is positive. Now, we can also relate this velocities, acceleration, time with the simple equations with the which are known as the kinematic equations for uniformly accelerated motion. So, let us derive the equations which are going to relate somewhat, we can say the initial velocity, let us say v naught, the final velocity v, time t, displacement x and a constant acceleration a. So, for this again I consider a situation, suppose a particle is moving between these 2 points. This is the origin, let us say this is the origin, right, and at any instant the particle is at this position A and let B be the final position. Suppose at this instant velocity is v naught and here we represent the final velocity as v. The time taken is t here, let us say. Suppose the time taken from position A to position B is t and the position is let us say x naught at point A and x at point B, and the time taken from A to B is t. So, using this information we are going to derive the equations, right. So, first of all, starting with the equation of instantaneous acceleration, we know instantaneous acceleration is equal to dv by dt. Now, proceeding further, can we write down it as A dt is equal to dv. Now, this tells the instantaneous situation. Now, suppose I want to know about the entire motion between point A to point B, then we are going to integrate it. We are going to integrate this equation. So, integrating the equation will be A dt, and then we are integrating the equation. For integration, we need the lower and the upper limits, that is the starting and the final situations. So, here we are going to take the limit of time as we are integrating with respect to time. So, the initial time is 0 and the final time is t, and here we need to take the limit of the velocity. So, the initial velocity we consider to be v naught and the final velocity to be v between point A to B. Now, if we integrate this A with respect to dt, then A will be considered as constant. So, actually we are integrating just 1 with respect to time. So, what we are going to get? We are going to get t, and this is how we have integrated. Put the limits over here. Here the integration of 1 means we are integrating v to the power 0. So, we get v itself, and then the limits are written as v naught to v. And now, substituting the upper limit minus lower limit, we get this is equal to v minus v naught. So, finally, we can rearrange the equation as v is equal to v naught plus A into t, and this is also known as the first equation of motion. Now, for simplicity, generally it is considered that the initial velocity is u. We represent initial velocity as u. So, here if we represent initial velocity, that is v naught equals to u, our equation can be rewritten as v is equal to u plus at, and generally the equation, the first equation of motion is used in this form, v is equal to u plus at, wherein u is the initial velocity, v is the final velocity, a is the uniform acceleration, and t is the time duration of that motion. Now, proceeding further, for the second equation of motion, we start with equation of instantaneous velocity. We know that v is equal to dx over dt. Again, it can be written as dx is equal to v times of dt, just cross multiplying, and at place of v I am just substituting the first equation of motion, that is dx is equal to v naught plus at into dt. Now, in the right hand side we have to integrate both the terms with respect to time. So, here integrating this entire equation, what do we get? Integrating dx is equal to v naught, again v naught will be constant with respect to time. So, just writing it like this, a is again constant with respect to time, we can say, right. For the small time velocity is constant, for the small acceleration is constant here only, right. Now, writing the limits, the lower limit is x naught, that is initially we have considered between the 2 points A and B, if you remember, we have considered this point to be the origin, this point to be the position x naught, and here we consider it to be x. So, the initial position is x naught at point A and the final position is x. So, the limits will be x naught to x. Here the limit we have to take for time, which is again time 0 to t and time 0 to t again. Now, when we integrate this equation, what do we get? Yes, on the left hand side we get x, integrating x to the power 0 with respect to x, and the limits will be x naught to x equals to again V naught is common, and we are going to integrate t power 0 with respect to time. So, we get t again 0 to t, then plus a, integration of t will be t square by 2. So, 2 is constant, I take it like this, and t square, and put the limit as 0 to t. Now, substituting the upper and the lower limits, we get x minus x naught is equal to V naught into t minus 0 will be V naught t itself, plus here we will get half at square. So, this is actually the second equation of motion. Again, for our simplicity, we can consider, generally we consider the initial position to be at the origin. So, here if I substitute the initial position to be at the origin, so we will say x naught equals to 0, right, and V naught equals to u. That is the initial velocity we represent as u. So, our equation takes a form as x is equal to ut plus half at square. So, this is how we represent the second equation of motion. Now, let us derive the another equation of motion, for which we again start with the equation of instantaneous acceleration, where we write a is equal to dv by dt. Now, in this equation, if I multiply and divide the right hand side with dx, it does not make any difference in the equation, right. Now, but what we can write down the equation as now, this dx upon dt can be considered as instantaneous velocity, right. So, I am just arranging the equation in this manner, this dx, changing the side of the dx, and then writing this dx by dt as v, and then this dv, right. Now, again I integrate this entire equation, acceleration, then integrating dx with the limit of x. So, here the limits are x naught to x again. The same limits we are taking is equal to integrating v with respect to dv, and the limits will be v naught to v, right. Now, this a is constant here for the small displacement, a is constant, a is otherwise constant also, it is a uniform acceleration. Now, the integration of x to the power naught, x to the power 0, the integration of x to the power 0 will be x, and the lower limit, upper limit here, integration of v with respect to dv will be v square by 2. So, we get v square by 2, and then again writing the limit as lower to upper. Now, substituting the limits, what do we get? A x minus x naught is equal to half, it will become v square minus v naught square, and this is actually termed as the third equation of motion. Now, again making our equation simple, we consider x naught to be 0 and v naught equals to u. So, the equation becomes now ax, and this 2 can be taken to this side. So, it becomes 2ax is equal to v square minus u square, or we can write down it as v square minus u square is equal to 2ax, and this is actually termed as the third equation of motion. Now, we can see that 3 equations are obtained using a simple condition, using a simple example of uniform accelerated motion. Now, these equations can be applied in different situations, in different examples of motion in which the body is moving with uniform acceleration, and the various other physical quantities can be determined. So, these are the 3 kinematic equations for uniformly accelerated motion. They are, the first equation is v is equal to u plus at, the second equation is s is equal to ut plus half at square, And the third equation is v square is equal to u square plus 2as, where the symbols are u is for the initial velocity, v for the final velocity, a for acceleration, t for time, and s is for displacement. So, we can use these three equations according to the requirement, according to the given situations in various examples of uniform accelerated motions. Now, let us recall what we have learned today. We have studied that the area under the VT curve represents the displacement over a given time interval. Next, we derived the three kinematic equations for uniformly accelerated motion, which are v is equal to u plus at, s is equal to ut plus half at square, and v square is equal to u square plus 2as.